Okay, guys, so I'm going to do this video real quick. This is phase 17, and I want to make a little connection here. So yesterday in the lesson, you were taking a look at like functions like this, accumulation functions. You were given the graph of the input, or not the input really, but of the function that's inside of the integral. And you were asked about like when g is increasing or decreasing and when f is positive or negative, and we saw this relationship. When g was increasing, f was positive. When g was decreasing, f was negative. And we've seen another situation like this, and that's in Susan's table. When we usually say like this is, so if this was g, this would be g prime. And guys, it turns out that in a situation like this, okay, if you've got an accumulation function, sorry for the blurriness, then it is the case that the derivative of it is what's inside of the integral. Okay, so that's a fact right there. And all right, so we're going to use that. We're going to use this to answer these questions. And we're going to use Susan's table also. All right, so let me say this basically. All right, so up at the top, I'll say if g of x is the integral from a to x of, I'll say f of w dw, then g prime of x is f of x, okay? So remember, this w is a dummy variable, so x is the input variable. So I just change it out right there when I write this as a derivative. Okay, guys, so over which intervals is h increasing? All right, so I'm given here the graph of m. H is defined as this accumulation function. Over which intervals is h increasing? Okay. Well, guys, if you think of this, if you look at this as a Susan's table, from a Susan's table perspective, and make this connection that m of x, that's equal to h prime of x. All right, so we need to make that observation right off the bat, okay? So when I'm looking at this graph right here, I'm looking at the derivative graph. I'm looking at the graph of the derivative of h. So what do you know about the derivative graph that would imply that h is increasing? The derivative graph would need to be positive. So I will say, so for part A, from 4 to 12, and then we need to be careful with our explanations because m of x is equal to h prime of x. So h prime is positive. Okay, now for part B, at which value or values does h have local maximums or minimums? Explain. All right, so for maxes and mins, you're looking for a sign change on h prime. So here I'm going to have a max or min, here I'm going to have a max or min. Now this one is going to be, at this point 4, h prime goes from negative to positive. At this point 12, it goes from positive to negative. So I can say min at x equals 4, max at x equals 12, right? And then I'll say because m of x is h prime of x, so at x equals 4, h prime changes from negative to positive, and at x equals 12, from positive to negative. Okay, now let's do this one. This time we've got the graph of q, and k of x is defined as this accumulation function with q inside the integral. So the first connection you've got to make, guys, is that q of x is actually k prime of x. All right, that's how these accumulation functions work. So part A, over which intervals is k concave down? So what would you have to know about the derivative graph of k to know that k is concave down? You'd need to know that k prime is decreasing. So for part A, the answer is going to be from 9 to 14 union 17 to infinity, because q of x is equal to k prime of x. So k prime is decreasing. All right, this is all Susan's table stuff. Which values does k have points of inflection? If you look at Susan's table, a point of inflection on the original function corresponds to extrema on the derivative. And I'll say, so I'm looking for extrema on this derivative graph at x equals 9, x equals 14, x equals 17, because q of x equals k prime of x, so k prime has extrema.